Drop down to the atomic scale, zooming through the rigid, three-dimensional grid of a silicon crystal. Eventually, you hit a dead stop, an interface. This schematic energy landscape represents that physical reality. It plots the conduction and valence bands as parallel, perfectly horizontal lines across the bulk of the material. This chart identifies the pervasive rubber sheet myth, the idea that these bands physically warp or sag in three-dimensional space. In reality, the diagram is an XY coordinate graph. It plots the potential energy of electronic states as a function of physical position. The curve of the band acts as a visible readout for the invisible electric fields operating inside the crystal. Every energy level shift follows a specific four-step causal sequence. The reaction begins with charge redistribution, mobile electrons and holes moving across the boundary. This charge separation establishes an internal electric field, shown by the E vector arrows. That field alters the electrostatic potential, directly shifting the electron's potential energy and bending the bands. Tracing this sequence allows for the precise prediction of how any semiconductor interface will behave. Before introducing any interface variables, we have to define the system's absolute constants. Rule 1. The band gap is a rigid structure. The conduction and valence bands are locked together. They cannot converge or diverge. They must shift up or down in perfect tandem. The second rule governs systems at thermal equilibrium. Equilibrium requires zero net carrier flow, which means the electron chemical potential must be uniform across the entire connected system. Because this potential is uniform, the Fermi level is drawn as a perfectly flat horizon line. This means all geometric variation in the bands must occur around this fixed horizontal Fermi level. To translate a spatial voltage curve into an energy band curve, we use a specific multiplier. Consider this generic electrostatic potential curve, or phi of x, inside a material. We apply the conversion equation. Potential energy equals negative q times phi of x. The negative sign represents the electron's charge. This creates an inverse mirror. When the electrostatic potential increases, the electron potential energy decreases, and the bands dive downward. Upward band bending in an N-type material indicates that electrons are being pushed away from the surface, leaving behind a depletion region of fixed charges. Downward bending indicates the opposite. Electrons are attracted toward the surface, leading to a state of accumulation. The bend's direction instantly diagnoses whether a surface is saturated with or depleted of charge carriers. Mathematical decoding allows us to extract precise physical data from the specific geometry of these curves. Flat horizontal bands indicate a region with zero electric field. The first derivative of the energy band, its slope, reveals the strength of the electric field. A constant geometric slope indicates a uniform electric field. When the bands curve, we apply Poisson's equation. The second derivative, the curvature itself, is driven by the local charge density. The density of ionized dopant atoms at the interface dictates the severity of this geometric curve. Drawing a band diagram is fundamentally an act of graphing Poisson's equation, turning invisible electrostatics into a readable geometric blueprint. We measure these shifts in fractions of an electron volt, but their impact on conductivity is massive. This exponential engine links carrier concentration to the gap between the conduction band and the Fermi level. An upward band bending of just 0.12 electron volts at room temperature seems negligible, yet that tiny shift results in a factor of 100 reduction in available surface electrons. This exponential leverage is what makes band bending the foundational mechanism of all modern solid-state electronics. This single mathematical model governs vastly different hardware applications. At a metal contact, Fermi-level alignment creates a depletion region and upward band bending. This defines the Schottky barrier, which controls how much current can be injected into the material. Inside a PN junction, differing dopant levels create a built-in potential, causing the bands to curve smoothly across the interface. Applying a forward bias reduces this geometric barrier, effectively turning the diode on. In a MOS capacitor, an external gate voltage actively bends the bands through an insulating oxide. Extreme downward bending creates an inversion layer, the conducting channel that allows a MOSFET to function. Diodes, barriers, and transistors are not separate phenomena, but different topological applications of these same geometric rules. The logic is consistent. Electrostatic potential dictates energy, electric field dictates slope, and Poisson's equation dictates curvature. Device engineering is simply the practice of manipulating hidden fields to shape these curves. To predict how a solid-state device will behave, stop looking at the hardware and start reading the slope of the bands.